and welcome to the to lecture 5 on Ramanujan Explained. Let me so just to know where we are. We have done approximately 26 entries of Ramanujan, and these entries are mostly about Q functions, Q hypergeometric series, and we've got some transformation formulas, and a lot of them came from Heine's method. And now I want to today the deal is to explain one particular limit. With this limit, we get a lot of hypergeometric series identities too. So hypergeometric, Q hypergeometric. This is like a hypergeometrics came first, then Q hypergeometrics came later. But what we are trying to sort of simplify some of the things. So, and also Ramanujan, his own work in hypergeometrics was a lot of it was a repetition of what had already been done, whereas the Q stuff was new. So we are taking the approach that we look at first the Q stuff and then take special cases and get the hypergeometric identities. And in taking the limit, this is the limit which works. So this is so Ramanujan put it right in the front as entry 1, a part of entry 1 in chapter 16. So chapter 16 is where the Q series happens, and this came in essentially entry 1, the second one. So this is the objective of today's lecture. Also, I want to I would like to start covering some of the background material. So some of it may be a repetition for senior mathematicians, but for students, I hope it will be helpful. Okay. So we recall the Q rising factorial notation. So this is 1 minus A, 1 minus AQ, and so on until 1 minus AQ to the K minus 1. K terms. So if we take the limit as Q goes to 1 in AQK, we will get 1 minus A, and there are K of that. Now this, of course, so what this means is that we can take limit Q going to 1 of AQ infinity over AQ to the KQ infinity. And now, since we've got these infinite products, we want Q less than 1, absolute value. And both sides of this equation make sense for, K replaced by X. So if we replace K by X, which is a complex number, so then it makes sense, and we can use the Q binomial theorem. And this we did earlier. We can use the Q binomial theorem to show that this limit AQ infinity over AQ to the KQ infinity, now let me call it X, is 1 minus A to the X. So this is this side can be interpreted using the binomial theorem, and this is actually entry. So in chapter 16, the first part of this entry which we are with. So if A equal to Q, there is a problem in taking this limit. So when A is equal to Q, you can't take this limit. Because as Q goes to 1, this becomes 0 raised to first. So this doesn't work. So when A is equal to Q, we formally sort of divide. So consider the limit. So let me call this f of x plus 1. And call this the limit as Q goes to 1 from the left. So we want, absolute value of Q less than 1. So Q going to 1 from the left, maybe Q is real, but for smaller values, essentially. And we look at AQ infinity, q. So replace a by q, then q raised per x plus 1, q infinity, and I divide this by 1 minus q raised to the power x. So what is this? What is this? This is essentially what we have. So let's just see what happens when x is equal to 0. So when x is 0, then this is q infinity divided by q infinity. This is 1, so you get 1. What happens when f is 2? Then it is limit as q goes to 1. When x is equal to 1, this is q square. So a lot of terms cancel. And you get 1 minus q over 1 minus q raised power 1, which is 1. So when x is equal to 1, right? And when x is equal to 2, we get 1 minus q square. And then here we get 1 minus q square. So, so this limit, one of them cancels, the other one will give you 1. And you can see that if you have f of n plus 1, then you get limit q going to 1. So when x is equal to 1, you get 1 minus q square up till 1 minus q raised to the power n. And here you have 1 minus q raised to n. And so there are 1 minus q over 1 minus q, 1 minus q square over 1 minus q. You get 1 into 2 into 3 up till n. So that's n factorial. So one can hope that f of x plus 1 is actually gamma of x. And this is actually what the identity is. Well, gamma of x plus 1. So gamma of x plus 1. So this is a conjecture, and this is in fact what the entry is. So let me write down the entry. This is in volume 3, chapter 16, entry 1, and second part. And this says simply that limit as q goes to 1 of q infinity. Now I'm putting q raised for x instead of x plus 1. Or I can just keep it x plus 1. So 1 minus q raised for x. This is equal to gamma of x plus 1. So that's the objective. How to derive this? Well, there are multiple ways, but this is something which we will need later to this approach. But let me define the gamma function. The Euler limit definition. So this is also a common definition used in special functions, and certainly Ramanujan was aware of it. So we define it as n going to infinity, limit as n goes to infinity of n factorial n raised for x over x plus 1, x plus 2, up to x plus n. So we will talk more about this a little later, especially we'll prove that this limit actually exists. But at present, let's just look at what a Q analog of this would be. So if you want a Q analog, of this, of gamma, then what would you do? You would, first of all, you would notice to get n factorial, well, that's easy. So you notice that limit as q goes to 1 of qqn over 1 minus q raised per n. So this will be the limit as q goes to 1 of 1 minus q over 1 minus q, 1 minus q square over 1 minus q, and so on. So that will be 1 into 2 up to n. So that's n factorial. So this part, the n factorial part, comes from here. Then to get n raised per x, that's easy. So just take this guy and raise it to the power x. So that will give you n raised per x. And in the denominator, you could take the limit as q goes to 1 of q raised per x plus 1 sub qn divided by 1 minus q. So this is going to give you x plus 1, x plus 2, up to x plus n. So putting all these three things together, you would want, so gamma of n plus 1 would be the limit as n goes to infinity, limit as q goes to 1 of qqn divided by 1 minus q raised per n, then 1 minus q raised per n raised per x, so 1 minus q raised per x. Then in the denominator, you will get q raised per x plus 1 q sub n over 1 minus q sub n raised per n. So this cancels. And let's assume we can interchange the limits. And we get what we want, actually, almost. Qn, 1 minus q raised per n over 1 minus q raised per x. And now if you take the limit as n goes to infinity, you will get what you want. 2q infinity over q raised per x plus 1 q infinity. And this term drops out. So you will get 1 minus q raised per x. So formally, it's not so difficult to obtain it. Of course, we have again, there's some pending agenda. We need to show that you can actually take this limit or limit exists or something like that. And then you can interchange the limits. So we will get to the formal proof, but right now I want you to understand somewhat formally what's going on. Okay, anyway, we define, so this is the definition of the Q gamma function, which is denoted like this, and it's defined as the limit, well, no limit now, q infinity over q raised per x minus q raised per x now, x plus 1, and 1 minus q raised per x minus 1. So, so obviously there are places where it's not defined, where the denominator, so the denominator is 0. You can see what those places are, and depending on the values of the x, it's kind of, you can figure out what exactly are the points where it's not defined. So anyway, but this limit is what is important, what we will be using a lot. So we are messing with infinite products, treating them as analytic functions of q, then taking limits as q goes to 1 and so on. So let's go back to a little bit of the theory. I will use this material formally, but we do want to at some point understand the theory so well that we can utilize, we don't worry when we are working in the area. But for now, if you want to just use it formally, then this is a thing to remember. So this business right here is the key point of this lecture. Um, and you can use it without necessarily understanding all the theory. But at least, but let's talk about the infinite product. So what I hope is that in this lecture, in the next, we cover a lot of the basics of infinite products, so that we can use them without worrying about them. And they're not so as familiar as infinite series for most of us. So that's the reason why I want to cover that. So let AK, I'm defining infinite products now. Let AK be a sequence. Consider Pn equal to product 1 plus AK, K going from say 1 to n. If the limit as n goes to infinity of Pn exists, and say equals P, some number P, and P is not 0, then we say the product converges. So this is this entire product 1 plus AK, K going from 1 to infinity, converges. So this P is not equal to 0 is an interesting new thing. And the reason why we remove P equal to 0 will become quickly very clear. So let's say if any one term, or at least one term, AK is equal to -1, and at most a finite number of them are -1, then we can and the product with these terms removed converges to P, which is not equal to 0. Then we say the product converges to 0. So we want, if there are finite number of 0 terms, we remove them in the product. And if the rest converges to something which is non-zero, then it converges to 0. Then we say it can be converging to 0, right? If it doesn't converge, we say it diverges. And if P is 0, so if the limit exists, but it's 0, then we say it diverges to 0. So obviously, when we have functions, we want things to be zeros, to have zeros, but we somehow don't want large number of zeros. We want only finite number of zeros. And if they're infinite, then at least in a region they should be finite. Okay, so necessary condition. The first condition which happens even in series, that if let's say this thing converges, 1 plus AK, this product K going from 1 to infinity converges, and I'm going to use the symbol, then AK goes to 0. So as K goes to infinity. So the proof is very easy. So we consider Pn plus 1 over Pn, the partial products, and that's equal to 1 plus An plus 1. And this, if it converges to something non-zero, this one goes to P over P, which is 1. And so therefore, this one will go to, so this implies that an plus 1 goes to 0. So this is a necessary condition that if this product converges, then uh, the nth term, the k term, converges to 1 plus 0. So it converges to 1. So this is equivalent, very similar to what we had in power. Okay, so that's the first theorem. The other, the second theorem is about, okay, so we know that we have a theory of convergence of series. How do we translate the convergence of products into the convergence of series? So there's a theorem that if no ak is minus 1, then the product 1 plus ak, k going from 1 to infinity, and the sum log 1 plus ak, k going from 1 to infinity, converge and diverge together. So this is the reason why we don't want ak to be equal to minus 1. And here, by log, we mean the principal value. So as a complex number, complex logarithm. So let me just remind you that we define log z as log of absolute value of z. So this is a real number plus I into argument of z. And in principle, argument of z can be anything, but if we stick to argument z bigger than minus pi and less than equal to pi, then we call it the principal value. Right. So basically, z is not 0. For 0, it's not defined because log of 0 is not defined either. And for anything else, we take this argument from here to here. So it's not continuous at, so not continuous at argument equal to pi, because here it's minus pi and here it's pi. So this is not continuous there. So if we delete this line, then log is a continuous and analytic function. So log z is, let's say log z is not continuous. Right, and in principle, so this is 1a, 1b. In principle, you could cut any ray, you could cut anything, any ray here, not containing 0, and you can take this values. So suppose you can take just, argument z to be bigger than alpha minus pi to alpha plus pi. To get the principal value. Again, equal to sign you remove if you want an analytic function. But otherwise, you can calculate the value, but the value may be different for different people calculate. The other thing I want to remind you is this um, the power series for z for the principal value. Something like this. Which is minus 1 raised power n minus 1, v raised power n over n, and going from 1 to infinity. And this is valid for absolute value of z minus 1. So this is 0, this is 1, and in this domain, not including the 0, log has this power series. This is the principal value. So this is the principal value, and the other values can be obtained by adding a constant here. So this is for the principal value. Other ones you can add some 2 pi I argument to get this. So essentially we are avoiding this guy. 0 is the word. 0.2 over it. The rest is okay. It's not a big deal. Okay, so let me prove this theorem. Um, so let Sn be the sum of log 1 plus ak, k going from 1 to n, and Pn is our usual thing, 1 plus ak, k going from 1 to n. You want to show that Sn and Pn have the same converge or diverge together. So first note that if you take the exponential of Sn, then we will get Pn. So whatever the values of logs we are taking here, we will get the same. When you take the exponential, it disappears, and we get Pn. So this is okay. So if Sn converges to S, then Pn converges to e raised power S, because the exponential function is continuous. It's analytics so continuous. I mean, analysis is differential, so it's continuous. Okay, so this part is fine. Conversely, suppose Pn converges to P, and we choose the so choose the principal value of P of log P. So I argument of P basically. Okay, and for any Pn, you choose choose the argument such that the log of the argument of Pn is between argument of P minus pi and argument of P plus pi. So so whatever the argument of P, if this is the argument of P, then you go from minus this to plus this. So you choose this place. Okay, so and of course log Pn is equal to log of absolute value of Pn plus I argument of Pn. So so what do we know? We know Sn is log of Pn. So this is fine. I mean, log of A plus log of B plus some Hn 2n by I. So plus some R. So this is you know, up to argument they should be the same for some n. So there's no n. Hn times 2 pi I. So they vary. So this Hn is some integer n. So they differ by some integer, and what we want to show essentially that Hn converges somehow. So we note that Hn plus 1 minus Hn times 2 pi I is equal to Sn plus 1 minus Sn plus log Pn minus log of Pn plus 1. So this is, so Sn plus 1 minus log Pn plus 1 minus Sn minus log n, and this guy will be log of 1 plus An plus 1 plus log Pn minus log Pn plus 1. Now, let's just look at the argument on both the sides. So let's just look at this argument on, I mean, this side is just Hn plus 1 minus Hn times 2 pi. So on the right hand side, this guy log 1 plus An plus 1, this goes to 0. And so of course, argument of 1 plus An plus 1. So this goes to 0 by our previous theorem. I mean, because the sum, because 1 plus An goes to 0. And argument of 1 plus An plus 1, therefore, is less than 2 pi by 3. Okay. And this guy, log of Pn minus log of Pn plus 1, we can write it as log of Pn minus log of P plus log of P minus log of Pn plus 1. So again, this guy goes to 0, this guy goes to 0. So again, this argument is less than 2 pi by 3. I mean, less than any random number, so you can just make it less than 2 pi by 3. So any arbitrarily small number. So this whole thing, we can see that the absolute value of Hn plus 1 minus Hn into 2 pi is less than 2 pi, or Hn plus 1 minus Hn is less than 1. So what does this mean? This means that Hn converges to H. So for some H. And some integer. Because this is an integer, HNs are integers, so the difference less than 1 means they're the same. So Sn converges to log of Pn plus 2h pi I, and that gives it. That does it. So what we are saying is, well, let me write it here. So if Pn converges, so does. So now let me continue. Right. So what this is said is simply that if you have an infinite product, anything about infinite products can be converted into this log series. They converge or diverge together, and this is really important to understand if you are looking at even Weierstrass products and so on. Why this form of log 1 plus AK puts some restrictions on the type of products that we are doing. So it fits in very beautifully with the Weierstrass theory, which we won't get into except, maybe sideways, but just as background. So anyway, an infinite product converges absolutely if the series summation log 1 plus AK converges absolutely. So this is your usual 1 plus AK converges absolutely. So we define absolute convergence in terms of this, and now we have a theorem. So I mean, we need absolute convergence as just like we need it in the series case. A lot of things happen very nicely, especially when we are talking about uniform convergence. Here's a theorem. The infinite product k going from 1 to infinity, 1 plus ak converges absolutely if and only if the series summation ak k going from 1 to infinity converges absolutely. So this is super convenient. Now we forget about logs. Well, here's a proof. We recall, note that the limit as z goes to 0 of log 1 plus z over z minus 1 is equal to 1. This follows from the, I mean, this is elementary calculus, but it also follows from the series for log 1 plus z. Um, so, and uh, if either the, so z is going to 0, if either the product or series converges, then an goes to 0. So this was true. So now we apply it here. So for n large enough, we have log 1 plus an over an minus 1 is less than, let's say, half for n large. And this means that log 1 plus an over an. So, I mean, it's between, let's say, half and 3/2. Right. So I mean, this is just saying that here is 1 and, take epsilon equal to 1/2. It's over here, this cap. And now it's easy to see that it's written too big. So now if let's say if summation uh, log of 1 plus an converges, absolute value, then we can see, bringing this guy, then we can see that summation of an is less than um, 2 times summation log of 1 plus an. So this converges. So summation an converges. Right. So by the comparison test, and also if you can take summation log of 1 plus an absolute value, this is less than 3/2 summation an. I mean, this converges. So if summation an converges, then summation log of 1 plus n. So this proves that both of them converge and diverge together. And this is brilliant because you have an infinite product and you convert it into infinite series. As far as we are concerned, this is really makes it simple. Okay, so let me show you an example now of where it's useful for us and really useful for us, in fact. So if so q is some number here, absolute value of q is less than 1, then zq infinity, which is the product of 1 minus z to the k going from 1 to infinity. So this converges absolutely for provided this is true, because summation q raised per k is less than 1. Right. So brilliant. You're not bothered about q equal to 0 because that gives you just 1 minus z. But beyond 0, anything, it converges. So this is really nice. That our Q products are absolutely convergent. In fact, you look at this as a analytic. So now we would like to look at this as a function of z. Once we know the convergence. So let's consider um, products of this form. One plus some function of z. So this is a k and k going from 1 to infinity. So of course there are issues at zeros of the factors. So there will be problems at this point, but we would for specific values of z. But we had the possibility of convergence at 0, but we would like functions to have 0. So if you look at functions of even this guy as a function of z, it has zeros at points where z is equal to q raised to minus k, right? So we usually we consider sets where there are finitely many zeros. And so obviously they don't have a limit point. And we study uniform convergence. So we study uniform convergence in regions. Region means in usual open connected sets where we do complex analysis. So where you can just delete these zeros, where such zeros can be deleted, and then later we can put them back. That is So the theory basically works out very beautifully if you remove the zeros. That's all. So if the series summation A and Z is uniformly convergent, in a region, so region is, the usual region, open plus connected set, then the product 1 plus A and Z is an analytic function. So we won't do the proof, but the proof is on the lines of what we normally do for series now, because everything works for series. So if there's uniform convergence and there is, in various sets of that region, it works very beautifully. no wait, I'm mixing things, is uniformly convergent in that region. So this follows from the previous guy. Now, if the A and Z are all analytic in a region and summation A and Z is uniformly convergent, then the product 1 plus A and C is an analytic function. So, well, we will do more of infinite products later because we still haven't done, I mean, we still haven't really covered everything, but I want to indicate some applications immediately, at least formally, one can do some applications. So, but let me show how you can apply these limits and get one result. So this was a result due to Ramanujan. I'm writing it like this. This was, I forget which entry, but the Q analog of the Gauss thing. So this is the sum, K going from 0 to infinity, A, B to infinity, K, sorry. In C to A and C over AB raised to power K. And this was equal to C over A, C over B, Q infinity, and C over AB to infinity. And this was valid for C over AB less than 1 and Q less than 1. Right. So we want to, what we want to do is we take A going to Q raised power A, B going to Q raised power B, C going to Q raised power C, and then take limit, the limit as Q goes to 1. So this will give us, this will double the number of results essentially that we have. So how do we take this limit? So we note that first of all, limit as Q going to 1 of Q raised power A QK divided by 1 minus Q raised power K. This is equal to, this we had just taken it earlier, but let me repeat it. So this is the limit as Q goes to 1 of 1 minus Q raised power A, 1 minus Q raised power A plus 1, go on, after 1 minus Q raised power A plus K minus 1. And then there are 1 minus Q's. And this limit is, or when you take the limit, you will get A into A plus 1 up to A plus K minus 1. So K factors. Right. So this we denote as A sub K. So let me say A sub K is the Pockhammer symbol, the rising factorial. Which is, so it's defined to be 1 if K is 0, or if K is bigger than 0, it is A into A plus 1 up to A plus K minus. This is also called the Pockhammer symbol. And what we have been using is called Q rising factorials. And so just note that 1 sub k is k factorial. So this also, it generalizes. So when when a is 1, then it's 1 into 2 into 3, so on until k. So it's k factorial. So LHS, which means this sum, what we're doing, we're dividing this by 1 minus q raised per k, 1 minus q raised per k, also dividing here, and we take limits. This is q is replaced, a is replaced by q raised per a, b is replaced by q raised per b, and so on. So the LHS goes to this Pockhammer symbol now, right? So which is so this is a sub k, b sub k over k factorial c sub k. So I'm just combining the two like I did in the Q rising case. And the RHS, if we write it down, we get q raised plus c minus a, q raised plus c minus b, q infinity over q raised per a, q raised plus c minus a minus c minus a minus b, q infinity. And I could use the q gamma function to write it like gamma q of c, gamma q of c minus a minus b, gamma q of c minus a, gamma q of c minus b. So you multiply and divide by various things. And now when you take the limit as q goes to 1, this goes to gamma of c minus a minus b. So formally, this limit that we did this time, it allows us to take limits of such ratios of infinite, q rising factorials. And what we get is, yeah, I'm sorry, I'll go maybe 5 minutes ahead extra. But what we get is, we get a result of Gauss from 1812, and Ramanujan recorded it as entry. So this is in volume 2, chapter 10, and it's entry 8. And this is summation k going from 0 to infinity, a comma b sub k, c sub k, k factorial. This is equal to gamma a, gamma c, sorry, c minus a minus b, and gamma c minus a, gamma c minus b. Right, and this converges. So we haven't shown this, but this converges when the real part of c minus a minus b is bigger than 0. And so the convergence is still this is still a pending agenda. So what I want to develop enough theory so that you can just look at it and decide what what it converges, where it converges, etc., and establish theorems for that. So that still requires some things. So along with this, there is a pending agenda of. So let me also mention that we still. I will cover gamma of z, the limit definition, in more detail. We will look at it again. I mean, so far we haven't even looked at whether it converges or not. I mean, whether the limit exists or not, but we'll do that and connect it with the other definitions. And let me just define hypergeometric series. As follows. So RFS, similar one, R numerator parameters, S denominator parameters. There's no Q, but there is a power series variable Z, and this is A1 to AR sub K, B1 to BS sub K, K going from 0 to infinity, and 0 is for K over K factorial. So this 1 sub K comes as K factorial, it's always there. And of course, A1 to AR sub K is the same as A1 sub K, A2 sub K, etc. So we'll still use it. And we will discuss convergence of this series later. And let me say that chapter 10 and 11 of Ramanujan's notebooks are on hypergeometric form. So we will cover that at some point. And right, so I think I managed to actually do it within an hour. So any questions or comments?